Good evening. I just found out that I am not going to be able to return your exams tomorrow. I am sorry about that, but it is out of my control right now. So I thought I'd let you know what we could talk about tomorrow. It's the next thing that we need to talk about. It's interesting too. We'll begin in the plane, and the thing I'd like to talk about is the difference between parametric and Cartesian presentation of information. So Cartesian means that you use the x, y, and z's to describe the object, and the object is a graph. So something like y equals x squared plus 1. And then the object that you look at is the graph of this. So the graph is all of the points x squared plus 1, where x is maybe in a restricted domain or the entire domain. Over here with parametric equations, we look at a function of a single variable that maps the real line into the plane. And in this case, we could look at this one, tt squared. And the object that we look at is the range, or the image that you get. Maybe here is also unrestricted. And these are the same in this instance. The range of this function is the same as the graph of this function. This is a function of one variable. And this is the kind of thing we take derivatives of functions, but this is a function too, so we can take the derivative here. Little different notation. But these are the objects of our study, a graph or this range. And we were interested in the geometric properties of those objects. And we can study in one or two ways. Now, this parameterization is called the graph parameterization of this graph over here. So this is the graph parameterization. I'll tell you what that means right now. It means you use the Cartesian variables as parameters. So in this particular case, there's just one Cartesian principal variable, input variable x, and that's going to be used as our parameter. So the t that we have here is replaces the x. It should have been t squared plus 1. And now the range of this function will be the same as the graph of this function. But there's a difference between the presentation and what you do with these things. So now let's take a little bit of look in two dimensions. So before we go, maybe I'll say that parametric has some advantages. They each have some advantages. But parametric has the advantage that an equation that isn't a function, if you look at this graph, this is not the graph of a function, but it has a nice parameterization. You can use 2 cosine t, 2 sine t, and it's a very nice parameterization of this curve. And so you can study the geometry easily without having to solve for y. If you solve for y, you could do it. There are two branches the square root of 4 minus x squared, and y is equal to minus the square root of 4 minus x squared. So in order to study this complete graph as a function, you need two functions to do it. And these are called branches. Branches of the inverse, actually. Okay, and the same thing is going to happen in higher dimensions. The parametric equations can describe a lot more, but if it is the graph of a function, then this graph parameterization can work very nicely. So the same thing now in one higher dimension, one dimension up. So we could look at the Cartesian equation, z equals x squared plus y squared. So in this case, we could graph this thing. Now you use different methods to graph. The graph, this graphs in 3 dimensions, so plot 3D is what you use. What you used the last time was just plot. Over here, to describe this parametrically, you need 2 variables now, s and t, and this indeed has a nice parameterization. You can use the graph parameterization in this case, let x be s, let y be t, and then z is s squared plus t squared. So there are other parameterizations we could use, but this is one. Okay, and maybe s and t are unrestricted in each. So this is again the graph parameterization of this curve. Here we are interested in the range, and here we are interested in the graph, but the object is the same. So let's do something with these. Let's find a tangent plane. And we can do it in both contexts. Over here, on the right, the thing that's easiest to find are the partial derivatives. So the partial derivative of this z, which is a function of x and y, with respect to x, is 2x. The derivative of z with respect to y is 2y. So the total derivative, z prime of x and y, is equal to the vector 2x, 2y. And these together with the original function are exactly what you need to find tangent planes. So if I gave you a point, like 1, 2, you would find the point on using this one. So maybe let's put that point on. Point equals the point 1, 2. And then on the graph, a point on the graph is 1, 2, and then the z value, 5. The slope in the x direction is given by this formula. So the slope of the tangent plane in the x direction is 2, and the slope of the tangent plane in the y direction is 4, 2 times this 2. And this is exactly the information you need to find the tangent plane. Over here, when you're finding the tangent plane, I used the graph parameterization, so a lot is the same, but this time we'll be given an s and a t. Let's again be given the same ones, 1, 2. Then the point on is 1, 2, 5, as it was before, a point on the object. The object is the same, but this time we will compute r prime of s and t. And so what will we get? We get a matrix where we have an s column and a t column. And I guess we only have one thing here. So the derivative with respect to s is 1, 0 to s. And with respect to t is 0, 1 to t. So now here is the derivative. This matrix, both of these are matrices, but different shapes here because of the nature of what we're doing. And so we are given now two directions. dir1 at the point 1, 2, when s is 1 and t is 2, is the vector 1, 0, 2, and dir2, the second direction at 1, 2, is the vector 0, 1, 4. So now what we're given is rather than just the slopes, we're giving these two directions of the tangent plane. And again, we can find the tangent plane. So the board is full. I'm going to erase, but I'm going to find the tangent plane in both of these instances. And maybe I'll just erase the top right here. Over here, the tangent plane has the equation z minus 5. So I'm going to use the point slope form. I have a point on and I've got the two slopes. So the slope in the x direction is 2. That will multiply x minus 1. Plus slope in the y direction is 4. And that will multiply y minus 2. So there is the point slope form. And it is a Cartesian equation. Over here on the other side, we will find the tangent plane. And now we've got a point, the same point, 1, 2, 5, but now we've got two directions. So the tangent plane as a function of s and t is equal to 1, 2, 5 plus s times the first direction, 1, 0, 2, plus t times the second direction, 0, 1, 4. So this parametric equation and this Cartesian equation describe the same object, the tangent plane. All of this is review, I guess, you might say. But now we're going to come to something that is a little different. Let's suppose we begin with a parametric equation, r of s and t, and it's not so simple. S squared plus t squared, st, t squared minus s squared. It's polynomial, it's a quadratic polynomial. You can graph this, but this is not so easy. This is not a graph parameterization. This is not an x. So this is different, but yet we can find, even though the Cartesian equation isn't so easy, what would you have to do for the Cartesian equation? X would be equal to s squared plus t squared, y would be equal to st, and z would be equal to t squared minus s squared. Theoretically, you can take these and solve for s and solve for t so that you can get a relationship between x, y, and z by eliminating the s and t variables. 3 equations, 2 unknowns, you should be able to eliminate s and t. Not so easy to do. We could eliminate the s by looking at x minus z. That would be equal to, or let's look at x plus z. That eliminates the s variable, and we get 2t squared. And t is equal to sy over s, but you can see that this is trouble. The solving these equations, even in the case of quadratics, can be a mess. But we can still easily find the tangent plane by finding the derivative with respect to s and t. The derivative with respect to s is 2s t minus 2s, and with respect to t is 2t s and 2t. So there is the derivative of this two-variable function. And now we can find two directions of this particular curve at any given point. So let's suppose we look at the point 1, 2 again. This will give a point on. So here we get 5. S times t is 2. T squared is 4 minus 1 is 3. So that's the point on. And then we have two directions. And this is the first direction, and this is the second direction at that point. So r prime of 1 and 2 will give you, let's see, 2, 2 minus 2. So that is one of the directions of the tangent plane. 2t is 4, 1, 4. So here we have two directions of the tangent plane. And so the tangent plane, as a function of s and t, is equal to the point on 5, 2, 3, plus s times, I could use 1, 1 minus 1 here, because any linear combination of these will be a direction of that tangent plane, and plus t times 4, 1, 4. So there's the equation, the parametric equation of the plane tangent to this object, the object being the range of this function at this point, 5, 2, 3. Could you find the Cartesian equation? You bet you can. I mean, we know how to take any parametric equation and find the Cartesian equation. Let's just do that. I'm going to erase here. The easiest one, so I'm after the Cartesian equation here of the tangent plane, Cartesian equation of the tangent plane. We have a point on 5, 2, 3. And we need some other stuff, either the slopes. We don't have the slopes, but we do have these two directions of the tangent plane, and they can be used to get the normal. So the normal vector is the cross product of 1, 1 minus 1 with 4, 1, 4. So now you have the point normal form. Once you get this, multiplying that out, you can get the two slopes. So this is what we've got so far, that in this parametric version, you go through the parametric version to get the slopes of the tangent plane in the x and y direction. Where are we going with all this? I'll try to give an example, maybe here. Here's an example of a plane. It's got a slope in the x direction and a slope in the x direction and a slope in the y direction. The x direction is out toward you, and this slope would be negative because you're seeing the flat 1 over how much down, and then the slope in the y direction is positive 1 over how much up. But it's also got a slope in any direction. So it's got a slope in the x, a slope in the y, but it's got a slope in every other direction. So we'd like to find those slopes in the other directions. So in the 1, 0 direction, so picturing this plane over, say, an xy space, that plane has a slope in the x direction. So if I go 1 unit in the x, the slope will tell you how far you go up. So this time I'm going to plot z out this way rather than straight up. I guess I could have done it straight up too. So if I go 1 in, let's do it this way. So if I go 1 in the x direction from any point, the question is, how far do you go up? Well, that's the slope in the x direction. Go up until you get to the plane. Pretending the plane goes through 0 and it goes through this point, then this little triangle will tell you the slope in the x direction. And then the same thing is true for the y. You go over 1, and then you go up a certain amount to get to another point on the plane. And then this is the slope in the y direction. That tells you that two vectors, this is the vector 1 in the x, 0 in the y, and then the slope in the x direction. This is the vector 0 in the x, 1 in the y, and the slope in the y direction. Now, if we're given a function like f of x and y equals x squared plus 3xy plus y cubed, and we're given a point on it, let's just be given the point 0, 0. No, let's be given the point 1, 2. When we find the derivative of this function, which is the derivative with respect to x, 2x plus 3y, and then the derivative with respect to y, 3x plus 3y squared, this gives you those slopes. So f prime of 1, 2 will give you the slope in the x direction at the point 1, 2, and the slope in the y direction at the point 1, 2. And from those slopes, you can get the from those slopes you can get the directions of the tangent plane. But what about other directions? What about if you go in a 45-degree direction? What is the slope of the tangent plane in that direction? And this is a unit vector in that direction. So now I'm using this capital D direction to be unit vector. What is the slope of the tangent plane in this direction? So I'll tell you how to do this. You take the derivative at that point. Oh, we haven't computed this yet. So 2x is 2 plus 3y is 2 plus 6 is 8. 3x is 3. Y squared is 4. This is 12, and 3 is 15. So the derivative there, this is called, by the way, the gradient in this case, is 815. So we take 815 and simply take the dot product with 1 over root 2, 1 over root 2. So you get 8 and 15, 23 over root 2. That is the slope in the 1 over root 2, 1 over root 2 direction. And this is called a directional derivative, where direction is a capital D direction, a unit vector direction. And no matter what unit vector you would take, this is how you do it. Okay, I think that's plenty for today. We'll talk about this tomorrow. I wish I had the exams to hand out. I do have the exams. I wish I had to be able to hand them out, but I cannot yet. So see you tomorrow. I don't even think I'm supposed to tell you that, but I did.